We had covered the theory of radiation. Now we are going to solve a few questions related to it. Okay. Uh, okay. Yeah. You can hear me clearly. Is the audio clear? Okay. Right. So just to make you recollect what you have learned, if you are talking about radiation emitted by your body, then the power emitted is given by E A sigma T raised to 4. And E is emissivity, A is the surface area, sigma stands for Stephen's constant, and T for the temperature. So let's solve a few questions based on this. Alright, so here's the question again. So if you have two spheres of copper, right? So material is same, but they have different temperatures. Now we are given that the radii are 6 cm and 3 cm respectively. So you have to find out what is the ratio of the power emitted by them. That is power emitted by the first divided by the power emitted by the second. Okay? I'm giving you a minute or so to try this question on your own. It's a fairly straightforward question. Right? Again, if you want to find the ratio of power emitted, you should use the Stephen's law. Okay? And try to find P1 upon P2. That is ratio of the power emitted. Let me just remind you that this is capital T, that is absolute temperature. Okay? So why don't you give it a try? I'll wait for a minute before I write down the explanation. Right? Also, if you can, you should try this question as well. Okay? About their peak intensities. Right? When you get the answer, you can type it in the chat box. I will have a look at what you got. I hope everybody is trying. No, they are spheres of copper. You don't need to treat them as black bodies, right? The Stephen's law is not valid just for black bodies. It is valid for every object, isn't it? Hopefully you remember that from the morning class. Is it done? Yes, Leah, you have to do that. Absolute temperature. I see the question is not about which peak is higher. The question is you have to find ratio of wavelengths also for that peak. First of all, you find ratio of power and then you find the ratio of those wavelengths. Yes, you have to convert to Kelvin. Absolute temperature. Okay, I'm doing it now. I'm not going to answer yet. Okay, here we go. Look at this. So, first of all, let's see what this is. P1 upon P2. So, for the first sphere, we are going to use this formula, and then for the second sphere. Emissivity of copper, we don't know, no problem, because both are copper, so the emissivity will get cancelled. A1, sigma is a constant, and temperature T1 raised to 4 divided by E A2 sigma T2 raised to 4. So you can clearly see that E and sigma will get cancelled. So this will be A1 by A2 and T1 raised to 4 by T2 raised to 4. Now we will simply put the value of A1. Remember, this is a sphere, and here when we write A, we mean surface area. Right? That's what we covered in the morning. That A stands for surface area. So first sphere has radius 6 centimeter. So 4 pi and 6 square. But actually we need to convert to meter, right? It is given in centimeter, we need to convert to meter. But because this question is about ratio, when you take the division, the units will always get cancelled. So as long as both units are same in this kind of question, it's okay. Similarly, A2, 4 pi 3 square, right? For A2. So A1, A2. Now time for T1 and T2. Now T1 is 27 degrees Celsius, but hopefully you remember that in physics we are having absolute temperatures, right? So this T cannot be the temperature in Celsius. It's capital T. Temperature in Kelvin. So 27 degrees Celsius converted to Kelvin is 27 plus 273. So that is 300 Kelvin. Right, and raised to 4 divided by, similarly, 327 degrees Celsius converted to Kelvin will be 327 plus 273, so that is going to be 600 Kelvin. Okay, so 600 raised to 4. So finding P1 upon P2. Here you get 6 and 3 cancelled, so you get 2, so 2 square, and then just like that 1 upon 2 raised to 4. So this power emitted, the ratio here is 1 is to 4, because 2 raised to 4 is 60, right? So this is the answer of the ratio of power emitted, 1 is to 4. So although the second sphere is water, right, but because it has less area, surface area, that's why the effect is not 16 times. Again, first sphere larger and cooler, second sphere hotter and smaller. So you know there is a balancing act going on over here. It's not exactly equal though, but it's in the ratio 1 is to 4. The next one, wavelength for peak intensity. Peak again stands for maximum intensity. So the symbol for wavelength for maximum intensity is lambda. So we have to find out the ratio of their lambda m's. Okay, we have to find the ratio of their lambda m. So let's say lambda m for 1 divided by lambda m for second. Okay, we are using the Wales displacement law. Again, the law is lambda m into t equal to constant whose value is b, or Wales displacement constant 2.9 in 10 raised to minus 3. Okay, so this is inversely proportional to temperature, right? This is inversely proportional to temperature, so we should just write T2 by T1. So T2 by T1, 600 by 300. So that's going to be 600 by 300 or 2. So the ratio of the wavelength for peak intensity is 2:1. Okay? So that's about this question. Right? Now let's go on with the next one. Okay. Now is the next question. Okay. So here is the next question, once again related to radiation. So suppose there is a sphere of hot gas in space. That is essentially what a star is, right? So let's say that there is a star, okay, which is having a surface temperature of 6000 Kelvin, right? Okay. The temperature on the surface, okay, is 6000 Kelvin. Now, gradually what happens is over the years, I mean many years, the stars expand, right? So it is found that the radius doubles. So this was initial, right? Let's say radius is capital R. Finally, it it expands and now the radius has become double, that is 2 1. Okay, so that's what is given. Now it is written further that the star emits or the gas sphere emits same radiant power. Same radiant power, that is the power emitted in the initial situation and the power emitted in the final situation is equal. Right? I repeat, power emitted in the initial and the power emitted in the final situation is equal. Then we have to find what is the wavelength at which it now emits maximum amount of radiation. Okay, so finally we have to find what is lambda m. Okay, finally we will have to find what is lambda m. Right? So you see what happens is that as the star will grow in size, its temperature is not going to remain the same. Right? Typically the temperature decreases, that is the star will cool down. So if you want to find what's the value of lambda m finally, right, if you want to find what's the value of lambda m, we'll have to find out what will be the new temperature on surface. Old temperature on surface already given, 6000 Kelvin. Right, now we want to find out what is the new temperature on its surface. Right, so you'll have to solve this question in 2 steps. First, use the idea that power emitted is equal. From that you will be able to find the temperature, and then once you find the temperature you can find what is the value of lambda m. Okay, so again between the first case and the second case the power emitted is equal. What is changing is the radius. Okay, right? So I want you to do the steps yourselves. Can you find what will be the temperature in the second case? Right? Then after we find temperature, we can easily find lambda m, because lambda m will be V divided by T. Right? In the second case. Okay, in the first case we don't need to find lambda m, it's okay. Right? Hopefully the method is clear. So why don't we get started from here? Just one note, be careful of the radius. The radius is not same. Right? And also, like I did mention in the class, we can consider a star or such a sphere of gas to be a black hole. Okay, so get started. Come on, I'm waiting for your responses. Uh, 4.2 Kelvin. Are you sure? From 6000 would it decrease all the way to 4.2? Rohan, I think you have made a little calculation mistake. Okay, right. So then you have to take square root twice, correct? That will give you the temperature. 300 Kelvin. Okay, everyone is getting different answers for temperature. let me do it then, up to temperature at least. So here, because the power is equal, so we'll start from there. Power is equal. Okay, power emitted will be equal. So here, E is 1. It's a black body, so it's okay if you don't write E. E is equal to 1. So A1 sigma T1 raised to 4 equal to A2 sigma T2 raised to 4. Because it's a black body, we are not writing E, or you can say we are putting E equal to 1. Now we will put A1 and A2. Radius doubles. So if the first radius is R, A1 is 4 pi R square. Sigma will be cancelled, and T1 given in question 6000. So this is 6000 raised to 4 equals. On the right hand side, A2 that is 4 pi, and now the radius is not R, it's 2R, right? Okay, W. So here we should be writing 2R whole square, that is 4 into R square. And T2 we don't know. So this is what we get. Right? I'm going to cancel whatever I can. 4 pi cancelled, R square cancelled. Okay, so that 4 remains. That's it. So we get T2 raised to 4 equal to 6000 raised to 4 divided by 4. Okay. We can do it in a calculator, but let's do it smartly. I'm going to take 4th root. Okay. 4th root, that is, I'm going to divide all the powers by 4. So here I shall get it like this. 4th root of 4. Don't worry about that. 4th root of 4 means taking square root twice. Okay, so that is easily root 2. I hope you got it. Did you get it, everybody? 4th root of 4 is nothing but root 2. Did you get it? Looks like you have. Okay. So 6000 divided by root 2 is what you have to do. Okay, so that we can easily accomplish in a calculator, right? 6000 divided by root 2. So that's going to be 4200 Kelvin. It's going to be 4200 Kelvin. So Resha, your answer was right, but probably you made a mistake with the point. Clear? Right, so T2 is 4200 Kelvin. Now, once we have found T2, let's go over to the next thing. We want to find what's the wavelength at which maximum amount of radiation is emitted. So, maximum amount of radiation is emitted at the wavelength which we call lambda m. We have to find lambda m. So, lambda m is equal to B upon T by Wein's displacement law. Okay, that formula, lambda m is B. So, 2.9 into 10 raised to minus 3 meter Kelvin divided by temperature, that is 4200. So you just have to divide. Okay, this is a single step, right? I'm leaving this for you. Don't forget to write the unit. Okay, the unit will be in meter, and then as you may require, you may convert it to nanometer or angstrom, whichever you like. Okay, so this is how you get this question, right? Again, I've been trying to give you a couple of questions related to these two laws, Stephen's law and the Wein's displacement law, right? Okay, because there is nothing given in your book, right? I searched it in the exercise, I couldn't find anything given. Okay, so this is what we have, right? Now we are going over to the next topic, that is Newton's law of cooling, right? I'm erasing everything here. Okay, Newton's law of cooling. Right. So Newton's law of cooling, as the name suggests, it's Newton again, right? And as it has been with many things, this law, when Newton first gave it, when Newton first stated it, this law was empirical, that is by doing observations of how bodies cool down when you put them in a room. Okay, how bodies cool down when you put them in a large room without any disturbance from outside. Okay, by observing such bodies he got this law. Okay, now there is the fact that this law is not so accurate, right? There is error in the law, right? But it is still valid, it is good enough. It is good enough to be used. It is valid for small changes or differences in temperatures. Okay, small changes or differences in temperature. For example, typically up to about 100 degrees Celsius. Right? I am not saying that this is correct. Remember, I only said that this gives a fair enough value, a proper value up to small changes or small differences of temperature. That is what we typically have when you heat something on a burner and put it in the room. Okay, it's not like you are going to use Newton's law of cooling to understand how sun cools, okay, or how earth cools down at night. That's a completely different story, right? So this is only valid in such circumstances, right? And even then, as the temperature difference starts to grow, you get errors, right? So remember, use it only for small changes of temperature, right? Okay. So now, what is the law? In its original form, the law is extremely simple, right? And you are going to find it very intuitive. The law is as follows. According to Newton, rate of cooling of a body, rate of cooling of a body is proportional to its temperature difference, is proportional to its temperature difference with its surroundings, Okay, this is as simple, right? Now what does that mean? Right, we can convert it to math, we'll get a better idea. First of all, rate of cooling. Rate of cooling means, let me just detail everything down here. Rate of cooling means how quickly an object cools. That is how quickly its temperature decreases. I repeat, rate of cooling means how quickly the temperature of a body decreases. If the temperature of a body decreases rapidly, we say it is cooling faster. On the other hand, if the temperature decreases very gradually, then we say it's not cooling that fast, right? So rate of cooling is mathematically this. Okay. Once again, differentiation. But if you remember, I told you earlier that now what happens is that rate always is a kind of differentiation. So what does this tell you? Forget the minus for a while. D capital T by dt. This means how the temperature changes, that is small change in temperature divided by small change in time, means infinitesimal time interval. Okay, d capital T by dt means rate of change of temperature with respect to time, d capital T by dt. Now what is the minus sign for? Listen, as time will pass, that is as value of time will increase. Remember, T is time. As value of time will increase, right? Let's say right now the time is over 5 hours and 25 or 30 minutes, I don't know exactly what's the time. Gradually as time will increase, the temperature of a body that is being cooled will decrease. Obviously, that's why it is called cooling. Cooling means decrease in temperature as time will pass. So, small t will increase, capital T will decrease. So, you know, dt and dt, they are small changes, right? I'm sure you remember that. dt and dt are small changes. So d small t is positive because value of time will increase, but d capital T is negative. I repeat, d small t positive because time will increase, right? But d capital T will be negative because temperature will actually be decreasing because the body is cooling down. Okay, so to avoid negatives every time, we need to write this minus sign. Okay, so rate of cooling is minus d capital T by dt. So for example, someone says rate of cooling is, let's say, 1 Kelvin per minute. Rate of cooling is 1 Kelvin per minute. What that means is every 1 minute the temperature will decrease by 1 Kelvin, right? Decrease. See, I said the word decrease. Decrease by 1 Kelvin, and that's what this minus is indicating, that the temperature should be decreasing with time. Nevertheless, that's about rate of cooling. So now what's here? Minus dt by dt, rate of cooling, is proportional to what? Its temperature difference with its surroundings. So let's say body's temperature is T, but surroundings temperature Ts. Then this is what the law is telling you, but often we don't write the minus sign here, we can put it over there also. So you can write it in either form, absolutely no problem, but don't forget to use the minus either here or there. Okay, this is fine by putting the minus sign on that side. So dt by dt proportional to negative of T minus Ts. T minus Ts means temperature difference with its surroundings. Okay, so you have liberty any one of them. And my personal preference is second. Okay, whichever you like. I'm going to pause over here, see if you have understood what we did here, right? If you have questions, you can ask. Hopefully you all do remember what is Ts, that is temperature of surroundings. dt by ds નથી, dt by dt છે. I said the minus sign is because if you are going to look at both these sides, let's say, right? Okay, look at both these sides. Object will be hotter than surroundings, obviously. Only then it will be cooling. I hope that makes sense, right? So right side is positive. Now if you don't consider the minus sign, what we have is that as time will pass, that means time is increasing, dt is positive. So if you take a positive here, but temperature will be decreasing, so negative upon positive, and on that side you have a positive thing, so negative upon positive, negative. To make it positive, we need a minus sign. Okay, it's not like if you don't write minus sign, everything is wrong. Then when you remove proportionality, you will have to get a constant. That constant will be negative. So to keep everything simple from the start, we say that dt by dt means rate of change or increase of temperature. But here we know that temperature is not increasing, the temperature is decreasing. That's why we write minus here. Okay, so that's what the minus sign is for. Okay, so this is the law, that's it, right? This is the law. Now let me just draw a graph and then we'll see if we can solve a question, right? So graph of what? Of T versus T, that is temperature of body versus time. Okay, again T stands for temperature of body. See what does this tell you? Rate of cooling is proportional to this difference. So at start, for example, at start, initially, that is when T equal to 0, right? Suppose surrounding temperature is 27 degrees Celsius, let's say, right? And the temperature of body, which is, let's say, quite hot, is, for example, 60 degrees Celsius. So you see the difference is 33 degrees Celsius. But gradually, as the body will cool, let's say after some time. Okay, like for example 10 minutes. Okay, for example after 10 minutes. In a large room, suppose you put some hot object in a large room, then the temperature of room will not change at all, or it will not change appreciably. That is, temperature of the room shall remain same, 27 degrees Celsius. On the other hand, the object would now have cooled, let's say after 10 minutes from 60, its temperature might have become, for example, 45. So you see the difference will decrease. First the difference was 33, but now the difference is only 80. Right? So what I am saying is that the difference of temperatures is decreasing. Now if the difference of temperature will decrease, the rate of cooling will also decrease. Okay, I repeat. At the start, difference of temperature 33 degrees Celsius. After some time, difference of temperature 80 because the body has cooled. So because the difference of temperature has decreased, the rate of cooling will also decrease. It means at start it cools fast, but gradually the rate of cooling starts to decrease. So what this means is at start the temperature starts to drop quickly. Again, temperature starts to drop quickly because this difference is more, the cooling is fast. But gradually, as you come from, let's say this is 60 to now, let's say you are at 45, for example. Okay, now the difference is only 80, not as big as 33. So that's why the rate of cooling also decreases, right? And now the temperature will change slowly. So that is what is going on. Ultimately, after a very long time, the value of temperature of the body will become 27 degrees Celsius. That is after a very long time, at theoretically at T equal to infinite, right? The temperature of surrounding will become equal to the temperature of body, that is the difference will become 0. But again, like I said, this is going to happen after a very long time. Okay? Key points here. Initially, temperature drops quickly because cooling is fast. Reason, the difference is more. Read that law. Later on, here the temperature drops or decreases very slowly because once again the difference between surrounding temperature, okay, and this one is less. Right? Do you have questions about this? Okay, can you all see till the end? Let me just turn this a little bit maybe. Can you see it now? Yeah. Any questions about the graph? What's the constant? Rehan, here the constant is not given importance. I mean, it doesn't even have a name, right? Okay, and when we solve the question, we will not even put value. The constant actually, in this, when we remove proportionality, the constant actually depends on what is the material of the body. For example, if you are thinking of cooling down of iron, then it would be different. And let's say there is some other thing like, let's say water, then that constant would be different. So here the constant will actually depend on what's the material, right? Okay, and a few more factors, right? But like I said, to use this law, you really never need to worry about the constant. Okay, so it's not given that much importance. It doesn't even have a name, to be very frank. We just write K, that's it. Okay, shall we proceed to solving a question? Yes, at infinity means after a very long time, the temperature of body and surrounding will become same. Obviously, right? Gradually it cools down and down and down. But temperature will not go below room temperature or below surrounding temperature. Correct? So that's why, it just touches that value, right? It just touches that value of the surrounding temperature. Again, these numbers are just for example. These could be anything, right? Okay. So that's the graph. Let's solve a question. Now, I want you to remember this fact. Okay, let me just make it clear. I'm going to write it. Okay, I'm going to write it. It's that all this, the Newton's law of cooling, the entire. Okay, excuse me. Just 1 minute. I dropped the mic. Just give me 1 minute. Okay, can you hear me, everyone? Alright. Yeah, so let's continue. I was telling you that all of this, in using Newton's law of cooling, please write that Ts shall remain constant. Okay? Only then Newton's law of cooling is true. Ts should remain constant, right? This is a condition. If that is not true, Newton's law of cooling is again not valid, right? So actually we have two conditions. One, temperature difference should not be that big, and temperature of surrounding should remain constant. Okay. What is barely? Hello. You can hear me, but barely. Is that what you're saying? Okay. It's better. So that's what we have. Now, what are typical questions? When we have an example in the book, but I think we'll do it later. Okay, it's already 57, right? Okay, I'm just going to wait here for. I'm just going to wait over here for your queries. If you have anything regarding whatever we have learned today.